Hey, good morning, everybody. This is Mr. Ainsworth here at Great Oak High School in Temecula, California, and we're going to get into the application of some exponential functions here. And so, the previous lessons, we talked about exponential growth and decay, and guess what? Here we are going to apply them. But before we get started, we need a calculator. So, we got to go over how to split screen. So, let's do that. We're going to swipe down from the top on your iPad, not like that. Okay, so hang on. Let's see here. There we go. Swipe down where you see the little menu at the very top and select Window. Select Move and Resize, and I'm going to put it on the left. Okay, there we go. I need Desmos, so let's bring it over here. So bring up the dock, press and hold on Desmos, slide it over right there, and then you want to resize the notes right there. You want notes to be big and Desmos to be small. Okay, I mean 50-50 is okay right through here. But I really don't like it that much because you don't, the graphing portion or the note-taking portion on the left is too small. All right, slide it over. All right, and then have your Desmos on the other side. Okay, so let's get started here. Go ahead and open up a new Desmos file, call it 2-7. So just type something in, select save, and label it 27. All right, just read the title up there. Applications to exponential functions. To exponential, you can abbreviate if you want, functions. All right, you can save all your work, and I suggest you do that. All right, so let's get started. Here we go. Number one, for her 8th birthday here, Shelly's grandmother gave her a full bag of candy. Pretty cool. Shelly counted her candy and found out there was 160 pieces in the bag, so that's the initial amount. So right there, that is your initial amount. So we have 160 pieces of candy. Again, this is called the initial value or initial amount. Okay? All right. As you might expect, Shelly loves candy. And so she ate half the candy on the first day. Look at that. So just reading through here, she ate half the candy on the first day. So we got to take half of this. So let's multiply it by 1/2, not plus, but times. Okay, this is times 1/2, and a half of 160 is 80. Okay, and if you don't know that, 160 here, all right, times 1/2, all right, times 1/2 is 80. Take a half of 160. 160 divided by 2 is 80. All right, and so obviously we have 80 here, 80, and then let's read on. Then her mother told her that if she eats at that rate, look at that, at that rate, you know, half the next day, the candy will last only one more day. So Kelly devised a clever plan. She will eat half the candy that is left in each bag each day. All right, and that's the key thing here. She will eat half of the candy that is left in the bag each day. That's a key concept right there. And she thinks this is the way she can eat candy every day and never run out. Ooh, okay. She thinks she can eat candy every day, okay, and never run out. Is she correct? Okay. How much candy here does Shelly have at the end of the week? And will the candy last forever or will it run out? Well, let's find out. Okay. So she's going to eat half after each day. So here we go. So we have to multiply by 1/2 again. So times 1/2, and half of 80 is 40. And again, you take 80 here, all right, times 1/2, or just so you can actually just take 80 divided by 2, and you get 40, right? Half of 40 is 20, and then half of 20 is 10. Again, we're taking half, we're multiplying by a half here, and 10 times a half, or half of 10, is 5, and then half of 5, well, that's 2.5. And if you don't know that, okay, you take 5 times 1/2, or 5 divided by 2, same thing, you get 2.5. Okay, so you get 2.5 pieces of candy. And then, well, let me see, what do you have? What's a half of 2.5? What's a half of 2? What's a half of a half? Which is 1 1/4. So let's multiply by 1/2. There we go. And a half of 2.5 is 1 1/4, or 1.25. So again, we're multiplying by a half because she's taking half, or she's eating half every day. That's what it says in the problem. So 1.25, or 1 1/4 pieces of candy. All right. Okay. Now, It says, what is the rate of decay? Of course, the numbers are decreasing here, and we are talking about decay rate here. This is a decay rate, and like in class here, I always tell you guys, if you always take y2 divided by y1. Okay, the first y value is 160, the second y value is 80, and the base, or the decay rate, which is your base, okay, call that b, is equal to y2 divided by y1, and this is 80 divided by 160, 80 divided by 160, and if you simplify this fraction, you cancel out the leading zeros, all right, you get 8/16, but guess what? 8/16 is 1/2, which is what we knew in the very beginning, okay? The decay rate is right here. It's the multiplication factor that you use to get to the next value. 160 times 1/2, or 1/2 of 160 is 80, and so on. So we kind of already knew that, but there you go. All right, and it says write an exponential function describing the situation. Well, you guys know that an exponential function in general looks like y equals a times b to the x power, where a equals the initial amount, okay, and b is your base. In this case, it's your decay rate, okay, or your in this case. Okay, so we already know the base. And we know, actually, let's highlight the initial amount right here. We know the initial amount is 160. So really, we could substitute 0, 160 in and find a, and we should know, though, that the initial amount, a, is 160 from previous lessons. Okay, so now what does this give us? It gives us y is equal to 160, which is our initial amount, times our decay rate, which is 1/2 to some power. All right, so again, this is our base, our decay rate in this case, how fast these things are decreasing, getting smaller over time, over days. All right, and then it says, using the function, how much candy will she have, on day 10 and day 15? Okay, so let's do this. Okay, let's put the function in first of all. So check this out. I taught you guys this in class. So y is equal to 160 times 1/2, right? Raise that to the x power. There's your function. I'm going to bring this to the top so you can see it better. Okay, notice you can do that in Desmos. Just press and hold with your Apple Pen and slide it up to the top. Okay, use your fingers so you can see the graph. And shrink the y-axis down so you can see the actual y-intercept up there at 160. All right, click on the gear, change your function to a table, get rid of the negative values because time can't be negative, and then go up to 7. Okay, and now you can see that the values that we created in the table are correct. All right, and if you want to graph it by hand, which I ask you to do, okay, you have to know what the scale is, and the scale is 10. 50 divided by 5 is 10, so 20, 30, 40, 50. So we have to find 160, which is up here, right? Not up there, sorry. So after 150, so this is 160. So plot a point at 0, 160. That is your starting amount there. And then after 1 day, you have 80. Okay, so that's about here. And then after 2 days, you have 40, half as much. After 3 days, you have half of that, which is 20. After 4 days, you have half of that, which is 5, so it's half of 10. Excuse me, that's 4. Okay, so I got to replot that. At 4 days, you have 10 candies left. So I got to go up to the first grid line here. There we go. After 5 days, you have 5, which is half of 10. After 6 days, you have half of that. So it's getting really, really close to the x-axis here, okay? And after 7 days, point 1.25 is barely off the x-axis. So when you graph this here, just go ahead and sketch it. This is a decay function. It's decreasing very rapidly, okay? And it'll never be 0, so don't go past the x-axis. Okay, so we say that it's asymptotic. It's a cool word here, asymptotic, okay, to the x-axis, which means it gets closer and closer all right, but never touches it. Okay, so interpret that, gets closer, closer and closer, but never touches the x-axis. Okay, gets closer and closer, but never actually reaches zero. But never reaches zero. So she's always going to have a teeny bit left if she keeps following the strategy. And by the way, that answers the question. I mean, will the candy last forever? You know, theoretically, yes, because there'll always be a teeny bit left. Okay, there will always be a teeny bit left. Not very much though. There will always be a very small amount left, like infinitely small. Okay, so small that she she won't really enjoy it very much. Okay, okay, and now let's finish the problem here. It says using the function, how much will she have on day 10 and day 15? So these are x values. So what is the y value? So when x is 10, so what's 1/60th times 1/2 to the 10th power? Well, just go to your table and type in 10, and it will tell you there's 0.156 uh, candies left here. So it's approximately equal to 0.15625 right there, candies, which is very small amount. Okay, I'm talking very small amount. And then the next one here, at day 15, here you take your function, 160 times 1/2, raise it to the 15th power. So just type in 15, it'll evaluate it for you. And you can see that, there's very little candy yet left, 0.004. I'm going to round this here, 88, which is, let's say, if we round that to 0.005, that's 5/1000ths. Okay, very small. There's a very small amount left. Okay, and this will never really be zero. I mean, you could put a big number in here, like a 1,000 maybe. All right, but that number right there is so small, it's infinitesimal. All right, so when you answer the question, not really, okay, not really. Mathematically, it really won't happen. There will always be a very small amount left. All right, but the amount that is left, the amount of candy left, all right, it is so small, all right, it's very close to zero. It is very close to, I'm going to say nothing, okay? It's very close to nothing. Zero. All right? So mathematically, in a situation like this, it will never get to zero because of what's happened. You always have half the amount remaining. But in reality, you guys, this amount is so small, she won't be really enjoying it for very long, okay? All right, click on the save button, save your Desmos work right there. And that, my friends, is one application of exponential functions right there. Look at that, that's pretty cool. We use some technology too. All right, we'll do a couple more here. I don't think I'm going to do all of them here because you got to obviously work on your own and learn how to do that, but I will go over just a few more here. All right, so check this out. So suppose you had $100 initially. Look at that, $100 initially. That's your initial investment at time equals 0. So let's put that in the table right off the bat. And you invested your money into a bank account that earns 10%, not $10, but a percentage each year. And the question is, how fast is it going to grow? And it says show how your money grows each year for the first 5 years. Well, to do that, to fill out the table, you have to interpret this right here. So let's talk about the growth rate here first. Like how fast is your money growing every year? Okay, so let's understand here. So there's a 10% increase every year. So first of all, let's understand that. It says it earns 10% each year. So 10% increase all right, each year. Let's just make sure we understand that. Because of that, at the end of each year, you're going to have 100% of what you start with, okay, 100% plus the percentage increase, plus the 10%, which means at the end of each year, this is at the end of each year here, you're going to have 100% of what you started with plus the increase. So at the end of the first year, you're going to have 110%, or at the end of each year, you're going to have 110% of what you started with. And what we need to do is we need to convert that to a decimal. Now, percent means per 100. Okay, percent means per 100. Okay, that should have been learned in the past. So just keep that in mind. Percent means per 100. And when people say 110%, that means 110 per 100. And if you don't know how to do that in your head, you don't know how to shift the decimal, you take 110 and divide by 100 on your calculator, and you'll see it's 1.1. Or you can remember basic arithmetic here, and you just shift the decimal 2 places to the left. Okay, so that's 1.10 or 1.1. You can just say 1.1. Let's make it simple. All right, so the growth rate, all right, your base, which is your growth rate here, B, is 1.1. So we need to multiply this by 1.1. That's your growth rate. Okay, so let's do that. So let's go to our calculator. All right, let's enter in $100 and let's multiply by 1.1. And notice we have $110 after 1 year. And then guess what? You multiply it by 1.1 again. So just multiply it right here times 1.1. All right, and you get $121. And then again, you're multiplying it each time by 1.1. So in your calculator, just go times 1.1, which is $133, right, and 10 cents. And then times 1.1. Every year, you have 110% of what you start with. So that's $146.41. And then again, you multiply it by 110%, which is 1.1. So again, times 1.1, which is $161.05. You got to round to the nearest hundredth here. You got to round to the nearest penny, as they say. All right, because we only have the smallest unit of money is pennies, right? You have 100 pennies per dollar, so you have to round to the nearest hundredth. Okie dokie. In fact, let's write that down. So round to the nearest hundredth. Okay, I'm talking about right there. Okay, second digit. And then it says, write the function, right? So you know your exponential function. You've been working on this extensively for a week now. So here we go. So what is your initial amount? Well, we know that we're given $100 initially. So A is 100. Okay, so we have y is equal to 100 times our growth rate, 1.1, right? 1.1 raised to the x power. There's our money function. All right, that's our growth of our investment. Look at that, growth of our investment in terms of money, dollars. Okay, and it says use your function to determine how much money you would have after 10 years. So remember, x is years, and y is money in dollars, your investment. So here, x is 10. So what does that give us in terms of y? So y is equal to 100 times 1.1 to the 10th power. What would that be? Well, there's different ways to do it. The simple way, one way to do it is you take 100, all right, times 1.1 and raise it to the 10th power. This is the first way. And we're going to get $259.37. We have to round it. Again, you always round to the nearest hundredth, as I was saying. And then when x is 15, okay, y is equal to 100 times your growth rate to the 15th power. So let's try that. So 100 times 1.1 to the 15th power. And we get $417, and look at that, 72 cents. Again, round that to the nearest hundredth. The other way to do it, I'm going to show this too, is you put your function in. So y is equal to, and this is what we've done in all the lessons in the past, right? 100 times 1.1. Raise that to the x power. There's your function. Now change it to a table by clicking on the gear. Right? Select table. All right, clear out the negative values because they don't make sense. Time's not negative. Right? And then you put in the right number. So we want 10 after 10 years, and we want 15 years. So just type them in, and there you go. And you see you get the same answers. Whether you type it in manually or, look at that, or using a function, using the table, you're going to get the same values. There you go. Now, when this deals with a percentage, so when you have a percentage increase, it's exponential. So when there's a percentage increase, okay, that indicates you have exponential growth. Make sure you write this down because this is, I'm not going to tell you on the exam, whenever you take one, what is linear growth and what's exponential growth. When I give you a percentage increase over time, it's exponential. When you don't have a percentage increase and you have a specific amount, well, that's probably linear, and that's still totally different. Which means we need to do number 3 because number 3 is totally different than number 2. All right, and then I'm going to end the video, and you guys can try the rest of the problems on your own and make sure you appear in class because that's where all the learning happens. Okay. All right, so here we go. And if you want to, if you're at home watching this here, pause the video. And then try it, and then when you're ready, press play. That's what I would do. Okay, and oh, by the way, press save on decimals. Save all your work. Okay, so now let's get started. Let's read the problem. So we have $100 initially. Look at this. But this time, each year you increase it by $10. So this is not a percentage. Okay, not a percentage. So this is a different problem than what we just explored. Okay, so we have $100 initially. That's your initial amount. AMT is amount. And it asks you to show how the money grows over the first 5 years. Okay, where X is years and Y is your money or your investment. Now it says it increases $10 per year, not 10%, $10. So here we want to add 10. Okay, add $10 every year. So plus 10. So you get $110 after the first year because it's an increase of $10, not 10%. And then you add 10 again. So plus 10, not times 10, plus 10. So it's 120 and then 130. And again, you're adding 10. So 140. So it's not growing very fast, is it? And then plus 10, all right, is 150. So it's not growing fast at all, not like what we saw up here. Here, it grew much faster, right? It grew about $11 the first year, and the second year it grew another over $11, and then, it's increasing faster that way. So growing by a percentage is always better. Okay, so notice something right here. The rate of change, which is $10 in this case, is constant. And this is what you guys were learning before. It's rate of change of $10 per year, right? It's constant, which means we have a linear function. And that means we use y equals mx plus b here and not your exponential function. So when the rate of change is constant, adding $10 per year, you have a linear function. And my first question is it growth linear or exponential? Well, as I just talked about, it's linear, okay? Right? Because the rate of change is constant. Rate of change is constant. All right, and that means we use this linear function called y equals mx plus b. Okay, where b now is your initial amount. Okay, so now this is your initial amount. It's your y-intercept. It's your initial amount. And then this, your rate of change, right here, this is your slope, or we call it m in terms of mx plus b. And that we already know is 10. Okay? So it says write a function that describes your investment. So if I know the rate of change is 10, okay, I have y is equal to 10 times x plus something. And then if you didn't know what that, if you didn't know what the b value was, your initial investment, you would plug in 0. You'd use this point right here, 0, comma 10, and you would plug it in. And I'll tell you what, I'll do the arithmetic. I'll plug in 0 for x and y for 10 if you didn't realize that b was 100 here. And then you would say, okay, 10 is equal to, no, excuse me, not 10, 100 here. 100 is equal to, let's start over. The initial value is 100, not 10. So here I have 100 is equal to 10x plus something, 10 times 0, excuse me, I have to plug in 0. All right, plus b, let's find b now. And of course, 10 times 0 is 0, and so 100 equals b. This is your initial amount. We already knew that though. Okay, and so your function, let's just write it here, is y equals 10 times x plus 100. This is a skill that you guys have been using or learning for quite a while now. Okay, so up here on your table, when x is 0, b is 100. Okay, that's your initial amount, your y-intercept. Your y-intercept. Okay, now it says use your function, your money function right here. This is your money function. All right, to calculate how much money you would have after 10 years and 15 years. So here, x is 10. So y is equal to 10 times 10, right, plus 100, which is 100 plus 100, or 200 bucks. And then when x is 15 years, y is equal to 10 times 15 plus 100. Well, that's 150 plus 100, and that's 250 bucks. Okay, after 15 years. So you have to really read the problem, and if you increase by a fixed amount, a constant amount, it's linear. If you increase by a percentage, it's going to be exponential. And you have to think about what you're doing. So in number 4, notice that you have 5,000 initially, and 20%, it grows, it earns 20% each year. That's going to be exponential. Whereas at number 5, if you have $5,000 initially and it increases by only 200, that's constant. All right, that's going to be linear. So go ahead and work on these. And again, I want you to, I'm going to stop the video here. So I want you to check solutions in Canvas. So check solutions in Canvas. That's where they're all located right through here. I'll post them in there. All right, because the video stops here. And then after that, go ahead and submit your work. So check solutions in Canvas and submit, all right, your work, as you guys always do. Okay. And again, let me just show you Canvas here. It's going to be, let's go full screen here. Let's go up here and let's go to Canvas. Okay, and go to, let's go, this is pre-calculus. Let me bring up the algebra here. So let's go into your Canvas here, go to 2.7 applications, and look at that, there are the solutions right there at the bottom of the screen. Okay, so you have a way to check your work, and hopefully this helped you out here. Get started on your application of exponential functions. Mr. Ainsworth here. Oh, look at that, the solutions are right up here. This is a hyperlink, by the way. So click here. So click here, this is a hyperlink for the solutions, and you can check everything. Okay, you can look them at them in Canvas, you can check them here. Man, you guys have so many tools. All right, so as with everything, do your best. All right, study efficiently. All right, use the technology efficiently, get good at Desmos, and I'll see you in class. Take care.